All right, now we're going to focus on energy in simple harmonic motion. Anything that goes back and forth in a cyclic motion like that is called a simple harmonic oscillator. When we talk about a mass spring system, that's the mass that's attached to a spring and it's bobbing back and forth. There's two types of energy that's in that spring. Obviously, there's going to be spring energy, and that's known as elastic potential energy. Elastic potential energy, or EPE, right? Elastic potential energy. That is spring energy. If there's a spring, it has EPE. That equation is EPE equals 1/2 kx squared. Remember, K is the spring constant. We already talked about what a spring constant is all about and how each spring has their own spring constant. And X is the displacement, the distance that the spring is either being stretched or compressed in meters, right? That's the unit for it. So that's the first type of energy, EPE. The second type of energy, since this mass is going back and forth, it's moving, so it also has KE, or kinetic energy. Kinetic energy. I'm sure you all know what kinetic energy is all about. Energy of motion, right? And that equals 1/2 mv squared. M is your mass, and that's always measured in kilograms. And v is your velocity, and that's always measured in meters per second, right? KE equals 1/2 mv squared. Remember, both EPE and KE are types of energy, and their units are joules, Joules, or just capital J. That's the unit. So the important thing to remember in a mass spring system, the two types of energy, like I said, EPE and KE. At any moment, the total energy of that system is equal to a combination of those two types of energy. And so total energy equals EPE plus KE, or E total equals 1/2 kx squared. That's the equation that equals EPE, and 1/2 mv squared, which is the kinetic energy equation. The total mechanical energy never changes. That's constant. The only thing that's changing is what type of energy it has at various positions. Oops, looks like the same slide. When we compress that spring, we squash that spring all the way down, right? You know its spring energy, or its EPE, is going to be at a maximum point. See it way up here? Way up here, maximum. Its velocity is 0 at that position, so it has no kinetic energy way down here. Remember, kinetic energy is 1/2 mv squared. So if it has no velocity, it has no kinetic energy when it's fully compressed. At that point, the total energy, or E sub t, is going to be constant because the total energy never changes. We move that mass spring to the equilibrium position. Now, at the equilibrium position, we're neither stretched nor compressing that spring. So EPE now is at 0. We're not squashing or stretching the spring. There's no more spring energy. If there's no more spring energy, that mass is now flying through the center of the equilibrium point. That's the maximum velocity. So KE is going to be also at a maximum. Once again, the total energy never changes. We're now stretching the spring as far as we possibly can. We know that it has tremendous EPE at that point. That spring wants to pull that mass back. So EPE is at a maximum and actually headed toward the left now, right? Kinetic energy, we went from a positive velocity and we're going to now go backward, right? We were going this way, and now we're going to go back that way. So we have to go through a 0 velocity. So kinetic energy is 0. Remember the total energy? Still constant. Question, at which location is the kinetic energy of a mass spring system a maximum? Remember, so kinetic energy is 1/2 mv squared. So we want to know, where is kinetic energy going to be at a maximum? Well, that's going to be where its velocity is at a maximum. Its velocity is at a maximum when it crosses the equilibrium point. At which location is the spring potential energy, or EPE, at a maximum, right? Well, that's either you're going to have tremendous spring energy when you're squashing the spring all the way or when you're stretching it. So that's going to either be at stretching the spring all the way or compressing it all the way. So D would be your best bet. At which location is the total energy of a mass spring system a maximum? Well, guess what? The total energy of a mass spring system, we said, never changes. At which location is the kinetic energy of a mass spring system a minimum? Well, there's not going to be any kinetic energy when its velocity is at zero. So where is its velocity at zero? At both ends, whether it's stretching the spring or compressing the spring.